Hi, my name is Faith Jean, and I will be introducing Intro Physics 2211 Lab Report 3 of a black hole. There are two parts to this lab. The purpose of part 1 of this lab is to find the mass of the black hole using the computational model glow script that simulates the gravitational forces of a star with a known mass and the unknown mass of a black hole. And part 2 of the lab is to find the initial velocity of the spaceship leaving a planet, to fly near the black hole, and to escape the black hole system without hitting the planet nor getting trapped in the black hole. The preliminary results of this lab resulted in the mass of the black hole being 1.246 times 10 to the 34th kilograms, and the initial velocity of the spaceship being negative 5.2 10 to the 7th in the x direction, 2 times 10 to the 6th in the y direction, and 0 in the z direction, meters per second. Key concepts in this lab include Newton's second law, which states a force applied to an object at rest causes it to accelerate in the direction of the force, which is illustrated by the equation F net equals change in momentum over change in time, which can also translate into the position update formula and the velocity update formula. Other key concepts in this lab include the parallel and perpendicular components of net force. The parallel component, P hat, is parallel to the direction of the motion and changes the speed of the object, and the perpendicular component, or N hat, is perpendicular to the direction of the force and changes the direction of the motion. In addition, gravitational force is at play, and that force is the force that attracts any two objects with mass, one typically being Earth. However, Earth is not one in this lab because we are in space. This is part 1's computational model, where we're trying to find the mass of the black hole. The system in this part is the star, while the surroundings are the black hole. The seed code is to create the unique trajectory of the star, and below it are the initial conditions such as the gravitational constant, the mass of the star, and the time that we will be using for observing the data. And on the right side, we have Newton's second law, as well as the parallel and perpendicular components of net force to figure out the net force, as well as net force perpendicular and net force parallel. So in order, we have the velocity components, the momentum components, finding the change in velocity, and then finally finding dp over dt, and then finding the dp over dt for F net, F parallel, and F perpendicular. As you can see on the glow script simulation on the right, the star orbits around the black hole. The orange arrow is the net force, the purple arrow is the parallel force, and the cyan arrow is the perpendicular force. The magnitude of all of these forces are on the slide. The mass found of the black hole was 1.246 times 10 to the 34 kilograms, and this was calculated by taking the average of all the masses generated in glow script. As you can also see in the video, the gravitational force is smaller in magnitude when the star is further away from the black hole versus closer to it, which is illustrated by the arrows. Possible sources of error when calculating the mass of the black hole could have been rounding done by the code, which could have caused the slight differences in mass, which is why the code generated so many possible masses. On this slide, we have the computational model for part 2 of this experiment, where the system is the spaceship and the surroundings are the black hole and the planet. On the far left side, we have the mass of the black hole, which was calculated in part 1, as well as other constants within the equations. In the center, we have the net force on the planet calculated through Newton's second law, and the net force on the spaceship due to Newton's second law, as well as gravitational force equation. And on the far right, we have how we're making the planet actually move through the position update formula and the velocity update formula, also Newton's second law. Through trial and error, an initial velocity for the spaceship was found to be negative 5.2 times 10 to the 7th in the x direction and 2 times 10 to the 6th in the y direction, meters per second, which is simulated by the video on the right, which shows the spaceship moving left and slightly up before getting shot out of the black hole system. The shortest distance between the spaceship and the black hole is listed on the screen. The space's gravitational force is at a maximum here, and the increase in force changes the speed high enough for the spaceship to be able to escape the black hole system. How does the net force and its parallel and perpendicular components relate to the rate of change of momentum and its components? Well, the net force is equal to the rate of change of momentum, which can be derived from F net equaling the derivative of the momentum over the derivative in time, which can translate to mass times acceleration, which is also Newton's second law. And the parallel and perpendicular components are also equal to the rates of change of the momentum, because the net force are equal to the derivative of momentum over time parallel plus the derivative of momentum over time perpendicular. If we wanted to make the spaceship orbit the black hole, the initial velocity through trial and error would have to be negative 2 times 10 to the 6 in the x direction, and 1 times 10 to the 7th in the y direction meters per second. And I had to increase the time in closed script to 3 hours to visualize the full orbit. The magnitude of the y had to surpass the x in order for this orbit to occur. Thank you for your time.